Okay. 1, 2, 3. I'm waiting. Mm-hmm. 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 I'm waiting. Mm-hmm.
We
Mm-hmm.
is lives.
Mm-hmm.
All
I'm
right.
waiting. Let's see what's going on in the universe. Lebanon conflict. Let's see this.
I really want to talk about this little clip here because oh god, it just rubbed me up the wrong way. It just pissed me off. Okay, Majority Report. I think this is in the context of their video about Ethan Klein and the Hassan Twitch drama. And oh god, it just really rubbed me the wrong way. Oh,
wouldn't justify it if there were gold under there. Who cares if Hezbollah has money? They're a political party in a different country. I mean, you can call them a terrorist organization. They're
what she's referring to is that the IDF had targeted a building in, I think it was in Beirut, that had Hezbollah hoarding money underneath it. And the problem is that Hezbollah is not just their political party with PAC money. Okay, that's not the issue. The issue is that Hezbollah's money is used to engage in activity that they are not legally allowed to engage in, even by Lebanese standards. They're not supposed to be an armed organization. The armed organization of Lebanon is supposed to be the Lebanese army. That's what they're supposed to be. Hezbollah is a criminal organization, even by Lebanese standards. They're not supposed to be armed. They're not supposed to be raising money to get more arms. Not to mention the fact that they're also drug traffickers. They are engaged in illicit drug trafficking with South American countries. They're also sex traffickers because in part of them helping Assad stay in power in Syria, which they did, they contributed to producing that Syrian refugee crisis. A lot of those Syrian refugees ended up in Lebanon. A lot of them ended up in Hezbollah territory because the border between Syria and Lebanon is near the Bekaa Valley, which is Hezbollah territory. So with a bunch of vulnerable Syrian refugees that some Hezbollah helped to create, they took a lot of those refugees and made them into sex slaves. They opened brothels in Lebanon. And this was caught not long ago. They caught one of the, I think it was the biggest sex trafficking operation in Lebanese history. And two of the people at the head of it were Hezbollah, high-ranking Hezbollah officials. So I don't know, to say they're a political party that has funds. It's so ignorant. It's so bad. It's mental. Anyway.
I mean, you can call them a terrorist organization. They're a resistance organization towards Israel. And I'm sure if I were to parse through the views of this resistance group as a cozy Westerner here in Brooklyn, that I would find many of their views distasteful. Perhaps they'd have an opportunity to update potentially retrograde social views as a political party in Lebanon if they weren't worried about Israel expanding their territory into Lebanon.
A belligerent neighbor
and bombing
invades them?
Yeah.
Whoa. So there's just so many different points to it's like the concentration of bullshit is. So the first thing she said was that it's easy to condemn some of their worst excesses and their distasteful behavior as a cozy Westerner. Which, it's ironic that she's saying that because again, it's cozy and Western of her to say that because from her perspective, they fight with Israel. Okay, so we don't need to hold them to the same kind of standard that you would hold, say, the Republican Party for their views, right? Because they're fighting with Israel. But that just means that it's her way of saying that they basically get a free reign to do all the crazy shit that they want to do in that country and in other countries because they occasionally fire off pot shots at Israel. And again, that's apparently acceptable because Hezbollah needs to be there because otherwise, Hezbollah's behavior is because of fear of Israeli expansion into Lebanon. It's so dumb in so many ways. Hezbollah is not there because they genuinely believe that had they stopped resisting, then Israel would just invade the south and settle it. It doesn't make any sense. Why did Israel leave Lebanon in the year 2000? They left. They unilaterally withdrew from the country. They were there for 18 years. Do you know how many settlements they built in that time? None. They did not try to settle in southern Lebanon. They didn't do that. They didn't even have to kick settlers out of their little shitty houses and bring them back because there weren't any there. There was just troops who were there. Why does Israel invade Lebanon? Well, in 1978, the first Israeli invasion of Lebanon was pre-Hezbollah, but that was when the PLO were there. The PLO were in southern Lebanon and they were launching attacks at Israel. The one that pulled Israel into the country was when the PLO went to northern Israel, they infiltrated northern Israel, and they attacked a bus that had like 30 or 40 civilians in it, and they killed them. They just killed I think 38 civilians in a bus. They like target buses because buses are a lot of people in a small space. You get high count. It's not been about Lebanese land.
Another reason to be against public transportation. It's a one failure point. It's like for the same reason that all central powers and it's always better to distribute everything, privatize everything, distribute everything. That's the problem with buses, with public transportation, with trains. They're always susceptible to attacks. Unions love attacking trains, shutting down the train. This is standard. Unions love shutting down public transportation. This is standard. And terrorist organizations love attacking public transportation. That's just another reason not to have plastic public transportation. Wait, can you hear me? I hope so. And by the way, Loner Box is Lebanese or half Lebanese, so he knows more than any of us what's going on. But you can rely on the white liberals to tell you, to disinform you, unfortunately.
I can just give you the breakdown of why this is so ridiculous.
You would think it would help that Loner Box is explaining to the white liberals that they're disinforming. This is actual dangerous and what do you call? How do they call it? This is harmful and dangerous disinformation. You would think Loanerbox uh, bringing up actual facts is going to cause these white liberals to rethink their position, to rethink. And also, there's a non-whitey. So you would think they would rethink their position. No, it's hopeless, and it's not just the white liberals. I've noticed this with conservatives too. It's everyone. It's the bandwagon, all the Jew haters, all the Zionists, the not Jew haters, the Zionist haters. It's completely different, you guys. It's not the same people. Only once in a while they have a slip of the tongue, and instead of saying Zionists, they say Jews. Yeah, they hate Jews.
When she talks about Hezbollah being a resistance group against Israel, she's referring to something that is definitely true historically. Hezbollah gained their initial growth and their initial reputation off of being seen as the ones who would fight off the Israeli occupiers in Lebanon. Because Israel was occupying Lebanon from 82 until 2000. And 82 was around the same time when Hezbollah started launching their first attacks. They became an official organization in about 85. When Israel invaded Lebanon, the problem was that the Shia population in the south was not well taken care of by the government. So a lot of them became refugees in their own country. They became displaced. And they didn't get the support from the government that they needed. So they were very increasingly isolated and abandoned. So against that backdrop, Hezbollah, with a lot of help from Iran, gets to come in and say, we're the ones who are going to take care of you. We're going to take.
That's not the reason. The reason is that Lebanon is a socialist country that has very little economic freedom. That is what stops economic development. Nothing to do with being ignored by the government.
Take care of your welfare. We're going to take care of your medical. We're going to take care of rebuilding houses if you lose your house in shelling or in a tank fire or anything. And we're going to be the ones who will fight the soldiers that did this to you.
All right, it's not going to help. It's hopeless.
When I was saying that the deep philosophical problem, I was actually referring to the question itself, because there are people out there, for example, there is this guy whose last name is Oppenheim, who thinks that you don't need to quantize gravity. I think you need a classical, that's a very semi-classical description.
So this guy Jonathan Oppenheim, what's
There are
his
people
name?
out there, for example, there is this guy whose last name is Oppenheim, who thinks that you don't need to quantize.
Jonathan Oppenheim. So he doesn't think we need to quantize gravity. I've heard him speak. I forgot his position, but it's ridiculous. He doesn't believe the universe is mechanical, and to him the universe is some Looney Tunes. The universe is some virtual reality, some mathematical, non-real, non-local, and complete nonsense. I couldn't make any sense. I feel very sad that the fact that he's a teacher in the world. This guy should not be teaching anything.
Gravity, I think you need a classical, that's a very semi-classical description where
So he's being paid to disseminate basically nonsense. I mean, literal nonsense, because he says the universe is under no obligation to make sense. He's one of those. So he literally disseminates nonsense.
your matter is quantized, but space-time is not. So what do you think about the question of quantizing gravity?
Oh, I see what you mean. I see. Well, I think that's not really a philosophical problem, so much as an empirical problem. I mean, the mainstream assumption in most of quantum gravity is that the gravitational field entangles with matter. So we know that if I put a rock over here, sorry, I'm starting to visually use it. I'll say that again. If I put a rock on the left side of my desk, then it gravitates, and passing particles are pulled very slightly towards the left side of my desk. If I put a rock on the right side of my desk, particles are pulled very slightly towards the right side of my desk. So how about now if I create a superposition of a rock on the left side of my desk and a rock on the right side of my desk? Well, what the mainstream assumption is that what that does is create a superposition of a gravitational field on the left side of the desk and a gravitational field on the right side.
But why is that only a problem with the gravitational field? Why is that not a problem with any other force? Right? You think that there is a superposition of the rock being both on the left and on the right, or two rocks, whatever. So before we consider gravity, you do agree that superposition agrees, and the rock is in both places at the same time, or whatever. Why is that? Why is only gravity suffering from this issue? Why not the rest of the forces? Why is suddenly gravity suffering? I don't understand.
On my desk, so that a particle moving ends up getting entangled by the gravitational interaction with the particle's location. The alternative might be that the particle is attracted not to the actual location of the rock, but to its quantum mechanically expected value. So the expectation value of the location of the rock is in the middle of my desk. And so that theory of gravity would say that the passing particle is attracted to
Anyway, this is nonsense. Physics today is nonsense. How to memorize and use the kinematics equation. What is that? What is a kinematics equation? What is that? What is this?
A Russian court has fined Google $2.5 decillion. Just how is Google going to pay more money than has ever been produced on planet Earth ever? Or is this actually just more Kremlin nonsense? And is the real victim the Russian public? I'm Paul, U.S. Army combat veteran. Let's get to the bottom of this stupid story. Okay, so the contours of the story are this. A Russian court has fined Google $2.5 trillion. And this is more money than ever exists in the entire universe. This is, of course, allegedly because Google has banned pro-Kremlin propaganda accounts backed by the Russian state media from its YouTube platform. The original fine was 100,000 rubles handed to Google in 2020, which under Russian law has doubled every single week, resulting in currently a fine of $2.5 decillion, right? Global GDP, of course, $110 trillion, worth noting that $1 in $5 is produced by the United States. No, sorry. But here's the thing. What Russian state media is reporting that, again, if the fine is not paid in 9 months, it'll begin to double every single day. And Google has said, quote, "We do not believe these ongoing legal matters will have any material adverse effect." This is from Google's quarterly results. Now, this is what I think is really interesting. One, Google already sort of was at odds with Russia because they were fined about $100 million in December 2021 for failing to take down content that Russia had banned, right? And again, Google, continuing to accrue these fines. Google, while they have had their lawyers fight it in Russian courts, the Russian courts have told them to pound sand. Now, there's a story here, and there's a real story, right? And yeah, $2.5 gajillion or whatever is pretty funny, but I think there's a couple of layers to this that are actually really important to discuss. The first of which is that you have to understand a baseline. In a Western country with strong institutions, right? The United States, Canada, France, the UK, Germany. What they are defined by is that their courts are independent from the central government, at least sufficiently independent that you can go and say, hey, I'm an individual. I think the government has wronged me. I think they, for example, let's say the police arrest you and don't read you your rights, and then
It's called separation of powers.
argue, right? You can go to a court, or let's say the police violate your civil rights. You can get a lawyer, you can go to a court, and that judge is going to look at your case, and he's going to look at what the cops say, and he's going to weigh the evidence. He's going to say, yeah, you know what? I think you were right. Even though the central government might prefer their police to always be right, I think they got this one wrong. And that applies even at the federal level, right? We see so often that companies say, hey, I think there was a bias in this multi-million dollar contract that the government awarded. I think they got it wrong, and I want to sue them. And a judge will hear them out, and often the government loses. In a place that is an autocracy, right, where it's dominated by a single individual or a small group of individuals, that doesn't happen. Those judges are appointed because of their loyalty to the central government, and they exist to enact the central government's will. And that's true in Russia. Now, that doesn't mean that if you get a traffic ticket in Russia, you can't fight it, right? You can go to court and probably you could spar with local cops and stuff. But if you're going to take on the Kremlin and and an instance where Putin and his oligarchs have an interest in the courts delivering a specific outcome, then the courts exist solely as a tool to deliver that outcome. And why is this so relevant in the Google case? Well, the answer is not because they're actually offended that Google banned Russian propaganda accounts. It's pretty clear that that is against YouTube's terms of service. And Russia has no meaningful way to collect any of these fines, let alone $2.5 decillion. But this is part of a larger Russian campaign, and this is the discussion that we have to have, right? If we look back in this is September, Russia began to throttle YouTube, which, as the Washington Post points out, is popular with young people, celebrities, and dissidents. And this is part of a larger Russian crackdown on what they perceive as alternative sources of online information. And this is this has been a problem for Putin since the start of the war, because remember, while Ukraine is fighting for its survival, and the Ukrainian people, they don't need a lot of outside information to learn what's really going on. The air raids, you can't miss them, right? And when your state is fighting for survival, that's motivation enough. But for Russia, this is kind of a war of choice, and Putin has an incentive. He needs, actually, Russians to feel like the war is a faraway thing, and that the Russian government is being transparent about the casualties. Officially, remember, Russia said they've suffered less than 10,000 killed in the war, but the reality seems to be closer to 10,000 killed every month. Now, if you go on YouTube, I can tell you, as someone who has publicly talked about these losses,
Welcome, welcome. I'm Kathy Mazak, and this is Academic Writing Amplified. I am so excited to get into our topic for today, which is how do you know that it's time to quit academia? Now, we have noticed in our programs that we are getting more and more people that are joining because they're trying to figure out if academia is even still right for them. And we offer programs to people who are professors. So it's not like we're talking about people who don't have the prestigious tenure track job. They have that job and they are asking themselves the question, is this right for me, or maybe should I quit? So this video is directed to you if you are a professor, whether you are in a tenure track institution like those in like many who have positions in North America, or whether you don't use the word tenure track, but you are full-time and permanent, which is kind of the language used in Europe and other places. This video is for you. Maybe you're feeling like, what did I get myself into? I'm not sure if this is right for me.
It is time to take out the trash, because this month there was yet another fake claim that a big announcement of the discovery of intelligent alien life is imminent from astronomers. And just to be clear, there's not. And I got so mad. Maybe it's just because this is the tip of the iceberg of so many fake discovery claims that circle the internet, especially when it comes to dangerous tea for some reason, which are all absolute, as the Americans say, trash. And this week, I have reached my limit, and I'm going to take it all out on BLC1, Breakthrough Listen Candidate 1, a radio signal detected back in 2019, which was already shown to be radio interference back in 2021. But this month, a documentary filmmaker claims to have spoken to someone at the University of Oxford who has links with the Breakthrough Listen project, who, yes, are hunting for signs of intelligent alien life in radio astronomy data, and he's claimed that announcement from Breakthrough at the University of Oxford about BLC1 is imminent. I'm an astrophysicist at Oxford, and I can tell you that me and my colleagues all laughed so hard at this news report. I mean, I did make sure to email my colleague, Dr. Steve Croft, who's the project scientist for the Breakthrough Listen project, and just double check, BLC1, you definitely concluded that was radio interference, didn't you? And he was like, yes, we did. So in this video, we're going to dive into everything we know about BLC1 and put these fake news rumors to rest completely. We'll start first with its detection back in 2019 and why it was initially thought to be a promising techno-signature of intelligent alien life, and then we'll chat about how it was actually ruled out as a real techno-signature and was instead radio interference, and then finally also chat about how no recurring signal has ever been detected since. And it's worth stating now that all of this information is also on the Berkeley website, the home of the Breakthrough Listen project, where they link to all of the research papers as well. And if there ever was an official announcement from Breakthrough Listen that they had found evidence of a signal from intelligent alien civilizations out there, then that's where the official announcement would be. Now, websites like this are all written in HTML and JavaScript coding languages. And I picked up these languages during my PhD, and I managed to use them to code up my own website. But if you don't know how to code, that can be a really big barrier to creating a website, either for yourself or for your business. But that's where Squarespace comes in, the sponsor of this week's video. Squarespace is the all-in-one website platform that makes it so easy to create a beautiful, professional-looking website. They develop what they're calling design intelligence, combining 2 decades worth of industry-leading design expertise with cutting-edge AI technology to help you build a beautiful, more personalized website tailored to your unique needs, which if you're like me without a single artistic bone in your entire body, you will greatly appreciate. Squarespace just makes all the difficult things about having an online presence just easy, from listing and selling products with seamless checkout processes for your customers, to email blasts, to analytics to track your hits and sales. So head to squarespace.com for a free trial, and when you're ready to launch your website, head to squarespace.com/Dr. Becky to save 10% off your first purchase of a website or a domain. So thanks again, Squarespace, for sponsoring this video, and now let's dive into everything we know about BLC1. And start with its detection back in 2019 by the Breakthrough Listen project, which is a dedicated survey of the 1 million closest stars to Earth for what's known as technosignatures, i.e. evidence of intelligent alien life existing. That's a very similar term to biosignature, which are the kinds of things we're searching for in the atmospheres of planets with the James Webb Space Telescope. So for example, a specific molecule that might be present in the atmosphere that indicates that life exists on that planet. That's any sign of life, whether intelligent or not, whereas technosignatures focuses on the technology side of things, mostly communications, so perhaps an advanced alien civilization that's sending communications between the ground on their planet up to satellites and beyond. So to keep an eye on 1 million of the closest stars to us, the Breakthrough
I just ate, so I want to sleep. Let me see some other. Okay, this we can close. Okay, let's watch this.
An electron or photon. Then we calculate its. How many times have you flipped a coin to decide something? We do it all the time. There's a 50-50 chance of landing heads or tails. We have no control over it. The result is totally random. Or is it? This is really not a random event. If we knew all the initial conditions, such as angles, forces, distances, etc., we could use Newton's classical mechanics equations to calculate the trajectory of the coin and predict with certainty whether the coin would land heads or tails. Newton's laws are deterministic. Given the same set of initial conditions, the result will always be the same. But what happens if we apply the same logic to an electron or photon? Can we calculate with certainty where we would find them? According to the most accepted interpretation of quantum mechanics, the answer is no, because its location is described by a wave function. And this wave function can only tell us the probability of a certain result. So the location we would measure would be probabilistic, not deterministic. There seems to be an innate uncertainty inherent in quantum mechanics. But is that really the way the universe operates? Is randomness built into the fabric of the universe, or is that just our interpretation? Some interpretations of quantum mechanics assert that the apparent randomness is due simply to our lack of information that is not accessible. But if we had full knowledge of all the information available in the universe, we could indeed predict the location where we would find that electron or photon. One such deterministic interpretation is Bohmian mechanics.
But you're assuming that the particle is a point particle, but in reality, it should be a wave.
Or pilot wave theory. But another intriguing idea takes the determinism of Bohmian mechanics one step further, and that is superdeterminism. In this video, we're going to look at what superdeterminism is by looking at what sets it apart from the plain vanilla determinism of Bohmian mechanics. Why do so few physicists accept it? What are the benefits and drawbacks? Is it real or is it a fantasy? I'll give you my opinion, but I know that many of you also watch my friend and fellow YouTuber Sabina Hassenfelder, who has some strong opinions about superdeterminism. She was kind enough to say a few words and provide a rebuttal to some of my views about it. You'll hear from her as well in this video. To break down what determinism is, then we can talk about what the difference is when we put the prefix super in front of it. Determinism is the idea that all events are predictable because they're triggered by events immediately preceding it. There's a cause and effect. So if we knew all the states of all the components of the universe at any one moment to infinite accuracy, we could predict everything that will happen in the next future moment, and the moment after that, and so on for all of eternity. Likewise, using the same logic, all current events could be traced to a cause immediately preceding it, and so on, backward through time, all the way to the beginning, up to the Big Bang. Quantum mechanics, however, seems to defy this kind of causal determinism because, according to its laws, identical sets of initial conditions can result in different outcomes. This is because the outcomes of measurements cannot be predicted in advance. We can only predict their probabilities. So, for example, when an electron goes through a double slit, we can only predict the probability of where we might find it when it lands on our screen. The actual
I'm actually not going to listen anymore to any quantum interpretations. I'm sick of quantum interpretations. I just want to see what we do know. Like, whatever we do know, that's all I care for. What we're not sure about, I don't want to hear about. I don't want to waste my time. There's plenty that we know. Basically, and I would say 99.99999%, many 9% of physics of the universe we do know. I mean, obviously we don't know dark matter. We know a little. I know a lot more than everybody about dark energy, but dark matter we don't know about. And but it's a waste of time to talk again about the confusion around superposition and entanglement and the interpretation of the wave equation. I understand it enough, so I don't want to waste my time with that nonsense. So let me close some browsers. Let me see what else we got. So this, I think, is a good video. Let's start this over.
As far as we know, there are four fundamental forces of nature. Gravity, responsible for keeping you planted to the Earth and the Moon in orbit. The strong nuclear force, responsible for keeping protons and neutrons bound together in the nucleus of atoms. The weak nuclear force, responsible for some kinds of radiation. And electromagnetism, which is responsible for light and chemistry. But remarkably, at the moment of the Big Bang, all these four seemingly different forces were thought to be one and the same. But as temperatures cooled and energies lowered, the forces separated into distinct interactions of their own. Gravity is thought to have separated first at some of the highest energy densities and temperatures. Then the strong force separated at cooler temperatures. What remained after that, at relatively lower energies and temperatures, was
What does it mean that these forces separated? We know that these are separate bosons. So what would it mean for these bosons to be the same and then later separate? I don't get it.
Electromagnetism and the weak force as one combined force called the electroweak force. Well, it turns out that the energies at which the electroweak force exists is something we can simulate in particle accelerators, such as the Large Hadron Collider in Geneva. And modern particle physics has a fairly robust theoretical basis that describes the nature of this combined force. But how could these two forces be one and the same at a fundamental level? Because at the temperatures and conditions we live in today, these seem utterly different and utterly incompatible. For example, electromagnetism is all around us in the form of light that we can see and chemistry that we can observe. It has infinite range and is relatively strong. The weak nuclear force, on the other hand, is pretty weak and something we can't directly see. It's effective at ranges smaller than the diameter of a proton. How is it that these two seemingly incompatible forces are one and the same at a fundamental level? It turns out that the key to uniting these two forces is something that was only recently confirmed to exist, and that is the Higgs boson. How the heck did we figure this out? The incredible story of the electroweak theory. Let me tell you what inspired me to make this video. I saw a fascinating document and how the featured some description of the function of the universe is represented by the standard model. I highly recommend time with no interruptions. Be sure to use a special link. I think you'll be impressed. The best theory we have about the makeup and function of the universe is represented by the standard model of particle physics. Think of this as the periodic table for elementary particles. These particles, along with their antimatter partners, represent all the elements by the standard model of.
It's a standard model of elementary particles and gravity. What do you mean and gravity? There's no gravity. There's no gravity. We don't have quantum gravity, so I don't know what they're talking about.
Particle physics. Think of this as the periodic table for elementary particles. These particles, along with their antimatter partners, represent all the elementary particles we know about. I want to draw your attention.
Oh, that's so interesting.
This is the periodic table for elementary particles. These particles, along with their antimatter.
Oh, that's so nice. So there's the particles, and then there is the antiparticles, which are identical except for opposite charge. Gluon doesn't have photon, Z, W don't have Higgs. So bosons don't have antiparticles, but the fermions, it doesn't even say that the left side is the fermions. Wait, so the bosons, the Z and the W, they have their mass from the Higgs, or some? I think they have their mass from the Higgs. No.
Partners represent all the elementary particles we know about. I want to draw your attention to the red particles. These are called gauge bosons, and they represent the mediating particles that carry 3 of the 4 fundamental forces of nature. Gluons mediate the strong nuclear force, photons mediate the electromagnetic force, and the W and Z bosons mediate the weak.
Wait, gluons mediate the strong nuclear force, not the strong force. Photon is electromagnetism. The Z, he's not saying what it's for. The W is weak nuclear force.
Weak nuclear force. Gravity is the fourth force that does not
Oh, the Z and the W is for weak nuclear. Okay.
currently fit into this model. You should be aware that there are actually 2 W bosons combined into one on this chart. There's a W plus and a W minus boson, which represent their electric charges. You might ask, what is a mediating particle? The exchange of virtual versions of these particles confer the appropriate force. So for example, when 2 electrons are near each other, their repulsion is due to the exchange of virtual photons. The simple analogy is illustrated here. The basketballs represent virtual photons. The boat represents similarly charged electrons. The exchange of momentum is what results in a repulsion, similar to the way the exchange of momentum of the basketballs results in 2 boats moving apart. Attraction is also mediated by photons, but it is analogous to the exchange of boomerangs and brings the 2 boats closer together. This is a simple analogy of how charged particles attract or repel each other. In either case, the mediating particle is virtual photons. The weak nuclear force also works by the exchange of a virtual W or Z boson. Let's take a look at perhaps the most important weak interaction, and that is the beta decay of a neutron. A neutron is composed of 2 down quarks and an up quark. An isolated neutron that is not part of a nucleus is unstable. On average, within 15 minutes, one of its down quarks turns into an up quark by emitting a W minus boson. This turns the neutron into a proton. This W minus boson almost immediately decays into an electron and an antineutrino. So what we detect in this decay is the electron and the antineutrino. The virtual particle is not detectable. The weak force is unique in this respect in that it is the only force which can change the identity of an elementary particle. In this case, a down quark becomes an up quark, resulting in a neutron turning into a proton. This is called a beta minus decay. Another similar decay called the beta plus decay turns a proton into a neutron. This kind of weak force decay is important in making atoms stable and plays a big role in nuclear fusion reactions that power the sun. The sun wouldn't shine without it, and we wouldn't exist. Let's go back to the chart of the Standard Model. You'll notice that the mass of particles are expressed in terms of energy, using the mass energy equivalence E equals mc squared, championed by Albert Einstein. You'll notice one big problem in uniting the electromagnetic force with the weak force, and that is the fact that photons are massless, but the W and Z bosons are massive, very massive. Their masses are about 80 and 90 giga-electron volts, or GeV. This is over 80 times the mass of a proton, which has a mass of about 1 GeV, or 1,000 MeV. So given the
So that means their force applies to a very short distance because of the Heisenberg's uncertainty that WE times WT is less than or equal to, or is it greater than or equal to H bar over 2?
differences between these particles and the fact that the weak force appears so different than electromagnetism, how did scientists realize they were controlled by the same guiding principles? Scientists, including American
So the photon is massless. That's why it works over an infinite distance. But what about the gluon? The gluon is massless. Shouldn't it work over an infinite distance? Great. SpaceX Live has a live. Let me see this.
Engineers never cease to amaze us with their incredible upgrades to the Starship system. We invite you to join in the celebration by flooding the comments with 100-F9. With this momentum, SpaceX is determined to maintain the Falcon 9's strong performance through the end of the year. So what do you think? Are 48 more launches feasible in this time frame? We'd love to hear your predictions and insights. Your engagement was paved with challenges and fascinating behind-the-scenes stories. Is crucial for future rocket testing and launches. Currently, the Massey Flame and encourage them to create even more captivating visuals in the future. Now let's delve deeper into the mechanics of this pioneering design. With nearly double the livable volume, it maintains the same trusted systems, but now heavy with the innovative Megazilla arm, a process continually refined since Starship Flight 5. There are reports that union workers will soon vote on whether to sign a contract with the company or continue their 6-week strike. This is understandable as the company's financial struggles cast doubts on its future 7th mission, debuting the second human-rated vehicle for the New Shepard program, the Uncrewed Verification Flight Center. Just days after that reveal, at the International Astronautical Conference, emphasizing capacity and functionality, confident in its capabilities, VAST has stated, VAST's design is projected to surpass all other proposed on-orbit space stations in terms of volume.
Physicist Sheldon Glashow had noticed some clues indicating that the weak force and electromagnetism could be related. For one thing, even though electromagnetism is millions of times stronger than the weak force at large scales, the theoretical strengths of both forces appear to be identical at very small lengths, about 1/1000th the width of a proton, suggesting a point where the two forces may merge as one. In addition, theoretical models predicted an additional gauge boson named the Z boson. This weak force boson would need to be neutral, like photons are. Glashow showed that an acceptable theory for the unification of the weak and electromagnetic interactions could be found, but the two forces had to be treated as one, as an electroweak force. And this model predicted 4 bosons that would mediate this force. Those bosons were the the W1, W2, W3, and B. There were two problems with this model. First, it predicted a third weak force boson, now called the Z boson, which was not predicted by any theory at that time. The first evidence of this particle only came much later, in 1973, with the detection of something called weak neutral currents. In addition, Glashow's model only worked if all four bosons were massless. It put the weak force and electromagnetism on equal footing, as both would have massless particles. One can call this masslessness a kind of symmetry. But ironically, this was a big problem because this did not fit observations. Something had to break the symmetry because the weak force was weak and interacted at only very small distances, indicating that its mediating bosons had to be massive. Glashow could not find a mechanism for making the four massless bosons from his electroweak theory into the three heavy weak nuclear bosons and the massless photon. You might ask, why do these gauge bosons have to be massive? Why does mass make a difference in the distance that the forces can act? This has to do with the Heisenberg uncertainty equation, which says that for virtual particles, the change in energy times
Because they knew the nucleus is small.
the change in time has to be less than h over 4
Oh, it's less than. Yeah, that makes more sense. Isn't it less than or equal?
pi. If we substitute mc squared for energy, we can see that the greater the mass, the shorter the time of the virtual particle's existence. So the short range of the weak force can be explained by the fact that massive virtual particles just don't exist for very long. Whereas for electromagnetism, since photons have no mass, they can exist theoretically for a long time and thus interact over long distances. So how do we reconcile the idea that photons and the W and Z bosons are ultimately similar and have a common origin if there's such a huge discrepancy in their masses? This remained a mystery. Glashow is even quoted to have said, "It's a stumbling block we must overlook." In other words, he thought his idea was right even though it did not fit observational data. 3 years later, in 1964, Robert Brout and Francois Englert in Brussels and Peter Higgs at the University of Edinburgh developed a mechanism whereby mass could be given to elementary particles while maintaining a meaningful theory. The Brout-Englert-Higgs, or BEH mechanism, employed the properties of a field, what is now called the Higgs field, to break the symmetry, and it predicted another massive particle, the Higgs boson. In 1967 and 1968, Pakistani physicist Abdus Salam and American physicist Stephen Weinberg independently took the ideas of the Higgs mechanism and combined them with Glashow's ideas to show how Glashow's three weak force mediating particles could gain mass, while the photon of electromagnetism could remain massless in the same theoretical framework. This is the basis of what is now the electroweak theory. Glashow, Salam, and Weinberg were awarded the 1979 Nobel Prize for their efforts. So now the question is, how does the Higgs mechanism give rise to masses in the three weak force particles, but not the photon? To illustrate this, I'm going to show a diagram that depicts the Higgs potential. The Higgs mechanism can, in a very simplified way, be understood by considering the Higgs potential. The Higgs potential gives the Higgs field the possibility of changing its effects. At energy scales above 160 GeV, the Higgs potential looks like this. This does not do anything because at the origin, the Higgs field interactions do not result in mass, and all symmetries are intact. However, at energies below about 160 GeV, the point at which electroweak interactions breaks down into two distinct interactions, the weak and electromagnetic, the Higgs potential begins to look much different. It looks more like this graphic. This is referred to as the Mexican hat potential because it looks like a sombrero. The z-axis is energy, and the x and y-axis indicate the vacuum expectation value. This vacuum expectation value becomes non-zero below 160 GeV. Vacuum expectation value is like the value of the Higgs field. This non-zero expectation value is what gives particles that interact with the Higgs field mass. As I've said before, all particles prefer to be at their lowest energy state. At energies of more than 160 GeV, the minimum of the Higgs potential is at the origin, where the vacuum expectation value is zero. In other words, everything is massless. But at energies below 160 GeV, the minimum vacuum expectation value is not at the origin. It is not zero. Thus, particles fall into the new minima. In other words, they obtain mass. You might ask, okay, why aren't all the four particles, including the photon, massive if this Mexican hat potential applies to all four Glashow particles? Well, to put it very simply, this has to do with the way the four particles interact with the Higgs potential. The simplistic explanation is that the photon remains at the bottom of the groove of the Mexican hat and does not have any other movement. It can freely move around this groove without needing any energy. And as Einstein's equation equals mc squared says, zero energy means zero mass. The other three particles, however, interact with the Higgs potential differently. They oscillate around the low point of the potential. This interaction with the Higgs potential requires energy as they try to climb the potential. Again, energy is equal to mass, and this is how they gain mass. So why is the electroweak force important? You have to realize that the reason we are where we are today in our understanding of particles and forces is due in no small part to the search for the Higgs boson, which was needed to explain the Higgs mechanism that united the weak force with electromagnetism, even though the two forces seemed utterly different. And this gives us hope that the next step in the unification, which would be to unite the strong nuclear force with the electroweak force, may also be possible, no matter how different these two forces appear to be right now. This unification would be the grand unified theory. And when we achieve this, the only missing piece of the puzzle towards a complete understanding of all forces would be a quantum level understanding of gravity, called quantum gravity. And when we unite the grand unified theory with quantum gravity, we will have the biggest prize in all of physics and probably all of science, the holy grail, the mother of all theories, the theory of everything. Let's keep going until we get there. I'd like to thank my generous supporters on Patreon and YouTube. If you have a question, leave it in the comments, and I will make every effort to answer.
I don't understand this.
This video is sponsored by Squarespace. Stay tuned to the end to find out about their special offer for Arvin Ash viewers. How many times have you heard someone describe a difficult concept as, it's not rocket science, meaning it's not as difficult to understand as rocket science is? Rocket science is synonymous with difficult subjects. Wouldn't it be nice to be able to say something like, well, I actually know rocket science, and I think this is more difficult than rocket science. After watching today's video, I think you may very well have the background to be able to say just that, because I'm going to show you how communication satellites work and how they are launched into orbit. Although there are several different types of satellites, these types are the ones that probably have the biggest impact on our daily lives. But to understand what these things do and how they're launched, you're going to have to learn something about, you got it, rocket science. And I'm hoping you'll find it's really not as hard as it's cracked up to be. That's coming up right now. Whether for your town or watch the national satellites owned by over 100 different countries orbiting the Earth right now, and thousands in directions, or if you've looked right now. If you've ever used a GPS app to find directions, or if you've looked up the weather for your town or watched a live TV broadcast from a foreign country, you have interacted with a satellite. Satellites affect our daily lives. There are almost 3,000 operational satellites owned by over 100 different countries orbiting the Earth right now, and thousands more are planned for. In 1687, Isaac Newton changed the way we humans view the cosmos by connecting a force we experience on Earth with the force that controls the movement of heavenly bodies. That force, of course, is gravity. And he expressed this analytically in a remarkable equation that is still used today, the law of universal gravitation. This equation explained the movement of planets, and it remains very accurate even today under most circumstances. But it had a few problems, one of which was the idea of action at a distance, that even Newton had trouble accepting. This was the idea that a massive object could exert a force instantaneously to another massive object at a distance without ever touching it. Later, in 1859, Newton's laws could not explain the rate of precession of Mercury, the way its elliptical orbit rotates around the sun and is not fixed. Newton explained gravity as an innate property of objects, a constant instantaneous force that could act over long distances. 250 years later, in 1916, Einstein changed this paradigm with the publication of the general theory of relativity. It solved the riddle of Mercury's precession and explained that gravity was not a mysterious force acting at a distance in the background of space and time, but was a result of a bending of the background itself, the curvature of space-time. It was a new paradigm that could explain more things. Today, 100 years after Einstein's publication, we find some holes in Einstein's theory as well, such as its inability to explain the singularity inside black holes and the Big Bang. One of the biggest pursuits in physics is the attempt to find a better theory.
There's no singularity in the middle of the black holes. Roll the credits.
A quantum theory of gravity. In order to understand quantum gravity, though, you have to first understand general relativity.
Stress. Okay, this is stress from stuff in space-time. Space-time curvature.
However, the mathematics of general relativity is so difficult that even a genius like Einstein could not easily derive it. And there's still papers being written today on specific solutions to these equations. I'm going to try to explain those equations to you intuitively and visually to give you an idea of what the math is trying to say. And I hope that this will help you better understand quantum gravity. That explanation is coming up right now. I watched a fascinating 2-episode documentary. It is a new type of science in space. I'll offer right now. Look at Newton's equation for gravitation. There's a link in the description. You will get a free 1-month trial. I highly recommend Magellan TV. Be sure to use the link in the description. If we look at Newton's equation for gravitation and Einstein's equation for general relativity, we see a remarkable correlation. For one thing, Newton's gravitational constant is present in both equations. In Newton's equation, we have a force on the left side created by mass on the right side. In Einstein's equation, we have the analog of force, the curvature of spacetime, on the left side. It has two components that describe the curvature and how distances in the curvature are determined. This is the analog of force described by Newton. I want to be careful here because in general relativity, gravity is not a force within the background of spacetime, like it is in Newton's equation, but it is a curvature of the spacetime background itself. In other words, gravity does not cause the curvature of spacetime, it is the curvature of spacetime. The right side of the general relativity equation tells us about the mass-energy content. This is represented by something called the mass-energy-momentum tensor. It's a source of the curvature. In the context of these equations, think of a tensor as a multidimensional array of mathematical components. This can be an array of vectors, scalars, or other tensors, and it's represented by an n by n matrix. A vector is a type of tensor represented by an n by 1 matrix. In general relativity, the dimensions are 4, so the vectors are 4 by 1, and the tensors are 4 by 4 matrices. So this equation describes what John Wheeler said so succinctly about general relativity. Space-time tells matter how to move, matter tells space-time how to curve. The right side is the matter and energy, which tells space-time on the left side how to curve. In return, the left side, the curvature resulting in gravity, tells matter on the right side how to move. Essentially, what this equation shows is that matter and energy results in a curvature of spacetime, which we perceive as gravity. Although this looks like one somewhat simple equation, it is actually 10 equations, and is very complicated mathematically. If we wrote down all the 10 equations fully, it would take up more than a page of text. A simplified version is shown here. It is so complicated, in fact, that Einstein was skeptical about being able to solve them. There are papers written to this day on various solutions to these equations. Let's take a closer look at what these equations are trying to say. The equations describe the curvature of spacetime by treating it as being flat at infinitesimally small distances. So you can consider that general relativity behaves like special relativity at these small distances with no bending or curvature. But overall curvature is taken into account. R, mu, nu, is the Ricci curvature tensor. It tells us how spacetime is deviating from flat. It tells you how spacetime curves at a given point. The second term on the left side is composed of R, the scalar curvature. It tells you how much the space is changed at any given point, such that you know how to correctly measure distances. Little g, mu nu, is the metric tensor. It tells you the geometry and structure of spacetime. Together, this term defines how distances are calculated given a curvature at any point. Note that sometimes a third term is added, lambda times g mu nu. Lambda is the cosmological constant. This term describes the intrinsic energy density of the vacuum or empty space. It's the mathematical expression for what we observe as dark energy, the accelerating expansion of the universe. It would comprise energy in opposition to gravity. Lambda is a very small number, about 1.1 times 10 to the negative 52 inverse meter squared. At small distances, this effect is largely negligible. On the right side, T is the stress energy momentum tensor, which tells us the density of energy and momentum at each point in spacetime. It is the source of the curvature. There's also a constant, which is equal to 8 pi g divided by the speed of light to the 4th power. G is Newton's gravitational constant, but this whole term is sometimes referred to as Einstein's gravitational constant. It's really just a conversion factor to make sure we get the proper units. The way these equations are formulated is by treating spacetime in 4 dimensions, 3 spatial dimensions and 1 dimension of time. This is incorporated in the mu and nu subscripts. The value of mu and nu can be 0, 1, 2, or 3. The 0 subscript conventionally represents time, and the 1, 2, and 3 represent the 3 spatial dimensions. This is why we have 10 equations. So for example, if we draw a matrix of all the values that mu and nu could have, we would see that there are 16 possible combinations. But this matrix is symmetrical. So 0 and 1, for example, is equivalent to 1 and 0. So if we take all the non-symmetrical combinations, we come up with 10 combinations, hence 10 equations. Let's look at what some of these combinations mean. So for example, one equation is where mu and nu are 0 and 0. 0 represents the dimension of time. What this would describe on the left side is the speeding up or slowing down of time at a point in space. And the right side would describe the energy at that point. Similarly, in another equation, the value of mu and nu can be 0 and 1. This would represent time in one direction and one spatial direction in another. So the left side in this case represents the combination of the stretching of time with one spatial dimension. The right side in this case would be the momentum or momentum density. In another equation, the value of mu and nu can be 1 and 1. This would represent spatial dimension for both mu and nu. In this case, the left side is describing the stretching of space in one of the dimensions. The right side in this case would describe the pressure at that point in space. The same can be said if mu and nu are 2 and 2 or 3 and 3. Here's a matrix of what the various combinations of mu and nu mean for the stress energy tensor. Note that the combination of the curvature in two different spatial dimensions is called shear stress. Is general relativity true? Yes, in general. For example, it predicts the bending of light around massive objects. This has been observed for our sun as well as...
No, this is predicted by Newton. You don't need GR for that. You need the correction, the two-factor correction. That's all.
Gravitational lensing around large clusters of galaxies.
That's available from Galileo already, definitely from Newton. So same thing. Bending of light gives you gravitational lensing. Again, Einstein just gives you a correction of a factor of 2. How do these people either spread disinformation or are misinformed themselves, which is, I mean, they're so smart, they know so much, but then they get this so wrong. I don't get it. Oh my God.
It predicts that time will run more slowly on the surface of Earth than on a mountaintop. This has been confirmed with atomic clocks. So why do we think that it's incorrect, or at least incomplete? The problem is that it does not fit with what is probably an even more accurate theory, and that is quantum mechanics. There is no theory that describes how gravity works at quantum scales, or even very small scales. Nobel laureate Steven Weinberg of electroweak theory fame said that no one should take general relativity seriously for distances shorter than about 10 to the negative 35 meters. So for example, let's take a simple hydrogen.
The wave equation just describes the way small particles are actually waving. Why? That I wouldn't say that's quantum mechanics. Quantum mechanics is the fact that there is quantum particles, that there are elementary particles. The fact that they are waves, fine. Okay, so there are elementary waves that make up this universe. Let me hear again what he said.
At least incomplete. The problem is that it does not fit with what is probably an even more accurate theory, and that is quantum mechanics. There is no theory that describes how gravity works at quantum scales, or even very small scales. Nobel laureate Steven Weinberg of electroweak theory fame said that no one should take...
That's not the problem. That is not the problem, because you can claim that Einstein's general relativity explains exactly how quantum particles behave gravitationally. You could say that Einstein made this prediction. You could say. Why don't you say that?
how gravity works at quantum scales, or this has been confirmed with atomic clocks. So why do we think that it's incorrect, or at least incomplete? The problem is that it does not fit with what is probably an even more accurate theory.
What do you mean it doesn't fit? What do you mean it doesn't fit? Well, why can't you fit it? An electron, like the attraction between two electrons, is exactly as Newton says it should be, or Einstein, it doesn't matter. Like, that's it. So roll the credits. What's the problem with that?
And that is quantum mechanics. There is no theory that describes how gravity works at quantum scales, or even very small scales.
Of course there's the theory. Einstein's theory can explain how two electrons attract each other. Roll the credits. That's not the problem. The problem is that it's not a quantum mechanical theory, regardless of the wave equation. It's just not about quantum particles. It's not about quantum mechanics. It's not a mechanical theory. It's a field equation, but it's not a mechanical theory. Same for Maxwell. Maxwell is not a mechanical. There's no photons. There's no mechanics. It's a magical. Oh my God. So it's not the problem that it doesn't explain. You could say that it does explain. It's just that it's not a mechanical theory. And these people, they're afraid to say it. They're afraid to say that, that's the problem. It's not a mechanical theory. It violates locality. It's spooky action at a distance. Newton's gravitation and Einstein's gravitation is spooky action at a distance. That's the problem, but they don't say it. Instead, they show the wave equation. Well, how is the wave equation relevant? How is the wave equation relevant? The wave equation has nothing to do with basically nothing to do with quantum. I wouldn't say nothing to do, but it's not the essence of quantum mechanics. It's not the essence. The essence of quantum mechanics is quantum field theory, is the Feynman diagrams. It's the interaction between elementary particles that gives us the behavior of the universe. The fact that we have a wave equation, that these things are really waves and they wave and so on, that's detail. That's not the meat and potatoes of the theory. The meat and potatoes is that there is these particles and there is especially gauge symmetry or gauge boson symmetry and particle exchange and virtual particles and Heisenberg, and so there's an entire mechanism by which we can explain what is light, what is magnetism. Like, these things are mechanically explained. That's quantum mechanics. That it's a mechanical, it's a localized theory. But there's no spooky action at a distance. There's no abracadabra and he turned into a butterfly. There's no spooky action at a distance. There's no the moon is somehow held by the earth remotely. That doesn't exist. In quantum mechanics, we don't allow for that. There's no spooky action at a distance in quantum mechanics. Quantum mechanics is mechanical, but these people deny it. They do have magic. I mean, everything is upside down. Everything is upside down with these people.
Nobel laureate Steven Weinberg of electroweak theory fame said that no one should take general relativity seriously for distances shorter than about 10 to the negative 35 meters. So for example, let's take a simple hydrogen atom, which is composed of one electron and one proton. Quantum theory says that the electron is in a superposed state, meaning it is in multiple positions at various distances from the nucleus at the same time. We only know that.
Obviously, that's nonsense, because you don't believe that, because if you entangle the electron with a cat, you don't believe that the cat is in multiple places at the same time or is dead and alive. So you don't believe that. So stop with the nonsense.
Probability of finding it at a particular radius if we were to measure it. Since the electron has mass,
yeah, if you were to measure it, then that's so nonsensical.
Into general relativity, it must curve spacetime, but it is in multiple locations at the same time. And the question is, where is the curvature? Is it also at multiple locations at the same time? We don't know.
What do you mean we don't know? You could say the same for everything, everything about quantum mechanics. There's indeterminacy. You can complain about everything else. Why do you only care about the curvature of spacetime? The curvature of spacetime. Oh no! Oh, we can't have that in multiple places at the same time. Oh no! Why? Why? Everything else, you have cats alive and dead at the same time. Why can't you have curvature of spacetime and not curvature of spacetime, both in superposition at the same time? Why? Everything else you're allowing. You live in a crazy universe. The universe is under no obligation to make sense to you. Why do you suddenly demand the universe to make sense to you when it comes to the curvature of spacetime? What's so special about the curvature of spacetime? I'm not even going to leave a comment. I'm so tired of these people.
There's nothing in general relativity akin to superposition like there is in quantum mechanics. A second problem occurs in the case of black holes. General relativity predicts matter and energy being compressed to an infinitely small point in space.
No, what are you talking about? What are you talking about? Schwarzschild assumed a point mass in order to derive his equations. He assumed a point mass. That is, by definition, a point of infinite density. That is a point of singularity. That's the assumption. That's not a conclusion. My God, I don't have time for these people. I'm wasting my time with these people. Just wasting my time.
with supposedly infinite curvature. But the theory breaks down here. If you go back to our original equation of general relativity, it's easy to see why it breaks down, since the equations treat space-time mathematically as being flat at infinitesimally small distances.
And Maxwell doesn't break down? How is it different than Maxwell?
And then calculate the overall curvature based on this presumption. A problem occurs when space is seemingly not flat at infinitesimally small distances. This occurs at the singularity, since it's supposedly an infinitesimally small point. So how do you calculate space-time curvature using flat space-time with an infinitely curved point?
There's no infinite curvature. You're welcome. Roll the credits.
Holding space-time. The mathematics of general relativity seem to describe singularities in this way, but
No, it doesn't. Roll the credits.
mathematical infinities like this are usually wrong. So there's probably something else going on here.
Yeah. Schwarzschild assumed a point mass. You're welcome. Roll the credits.
Just haven't figured out. There are some other issues as well when you try to integrate general relativity with quantum mechanics, such as the problem of information loss due to Hawking radiation. The bottom line is we don't
Hawking radiation is wrong. Roll the credits.
really know how gravity behaves at quantum scales. General relativity has been tested to scales of about 1/10 of a millimeter. At atomic scales and below, there's probably some better theory that will describe it. The problem is that quantum mechanics works fine with space-time curvature as the background. The problem with gravity is that it is not something that works with space-time curvature as the background. It is the space-time curvature. Space-time curvature is gravity. Do we have anything?
That's no. No, there is no space-time curvature. Roll the credits.
That comes close to describing gravity at really small scales? There are two theories that seem to be promising: loop quantum gravity and string theory. And these will be the subject of my next video. So stay tuned. You won't want to miss it.
Yeah,
I'd like to thank my
I want to miss it. I really want to miss it. I don't want to waste my life. No one is listening to me. No one is listening to me.
Reports on Patreon and YouTube. If you like my videos, consider joining them. And if you have a question,
I mean, I like his videos, but most because he's so straightforward that you can tell the nonsense. I mean, altogether, it's a waste of time to watch his videos. I don't know. I don't know what to do with this guy.
you can get a glimpse of the vast universe around us. It's amazing to think that on a dark night away from city lights, you can get a glimpse of the vast universe around us. It's amazing to think that every star, planet, or structure that you can see is controlled by the same force, the force of gravity. And it is this force that binds stars to galaxies, planets to stars, and us to the Earth. We've been aware of this force for a long time, and thanks to Isaac Newton over 350 years ago, we got the first mathematical model for describing it. His equation contained a constant now called Newton's gravitational constant, G7. His theory allowed us to model the solar system fairly accurately, but over time we found that it was incomplete because it gave us some wrong results. In 1915, Einstein gave us its successor, general relativity, which fixed the issues with Newton's universal law of gravitation. It allowed us to describe new exotic phenomena, such as black holes, gravitational lensing, and even build a model for the entire universe called the lambda CDM model, sometimes colloquially referred to as the Big Bang Theory. However, we find today that general relativity is also incomplete. Since Einstein's great insight, we have come to find that the universe, at its core, seems to be quantum, not classical. But general relativity is classical. So we find that if we try to use Einstein's theory to make a meaningful quantum model of gravity, it gives us nonsense results. This has led some to question whether a quantum model even exists. Why is this such an intractable problem? In fact, the most difficult problem to solve in physics. And given how well general relativity works, is such a quantum model of gravity even necessary?
Why is it any different than Maxwell's equations that were quantized with quantum mechanics? Why would there be a problem quantizing GR? I don't get it. What are these people talking about?
Instead of trying to force fit general relativity into the framework of quantum mechanics, why can't we do the opposite? That is, fit the other three forces into the framework of general relativity. In this video, we'll answer the
GR is classic. It's not mechanical. It's not localized. Yeah, we are looking for a localized theory.
questions, as well as look at intuitively what happens when we try to quantize gravity. Why quantizing gravity is such an intractable problem. And we'll review two of the most popular approaches to quantizing. That's coming up right now. Is a quantum theory of gravity really necessary, or are these government-funded research programs simply providing jobs to physicists for no good reason? Why
didn't I listen to this already?
We quantize the gravitational field. Keep that question in mind, but the short answer is there are some good reasons. First of all the other fields in nature are quantized. There's a sense that there's nothing
That's
special.
not a reason. Jesus Christ. Okay, I don't want to waste my time. Why are these windows still open on my laptop? Oh, I lost the connection. Let me see. Whatever.
Scientific concepts to grasp is Einstein's theory of relativity, and in particular, how gravity can be. One of the more difficult scientific concepts to grasp is Einstein's theory of relativity, and in particular, how gravity can be explained by way of curved spacetime. Today, my goal is
You
to
see, he's showing the flow. Something is flowing
understand it in less than 10
into
minutes.
Earth. So you see that he's interpreting GR as a flow.
We'll be using diagrams that show time on one axis and one dimension of space or distance on the other. The diagram establishes a frame of reference that measurements can be made against. For now, pretend that gravity doesn't exist and everything is floating freely. This is the realm of Einstein's special relativity. If an object is at rest in your chosen reference frame, it's traveling through time only and not traveling through space. If it's moving at the...
I'm too tired to listen to this nonsense.
Loco, loco, suono loco, 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 ritmo loco, loco, loco. Loca, 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 chica loca, 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 muy golosa, loca, loca, vanitosa, loca, loca, vanitosa.
Dude, have you seen Simon Cowell recently?
Yeah, what's going on with him?
I don't know, man.
He used to be a good-looking guy. Like, what happened? What? His like eyes are sinking. His forehead looks Botoxed. Looks like he's got some fillers in his cheeks. Look how good he looked back then.
Yeah.
Handsome. Jesus.
Okay. That's probably a generous picture compared to some of the ones I've seen. Dude, have you seen Simon Cowell?
He's old. Maybe, I don't know. Maybe he lost weight.
Take this. Take this. Take it, please.
Oh my god. What did he do? Did he eat the crab? Wow, that's fast.
Okay, decrease me there. What? No, leave me alone. Leave me. Put me down. Yes, I stay here in the Kotane, but this is home. Oh, home. Me stay here. Bus stop. Bus stop. Yes. Okay, decrease me there. What? No, leave me alone. Leave me. Put me down. Yes, I stay here in the Kotane, but this is home. Oh. Home. Me stay here. Bus stop. Bus stop. Yes.
Did you have the video on?
Yeah.
Oh, good. Watch it. What? Check it out.
This is how I find my boyfriend when we lost each other in a mall.
When I first met him, he was super loose and relaxed. He brought me a blowtorch in my studio, firing off this flamethrower with 17 feet of fire coming off the end of this in the middle of our lobby. And I'm like, what the f-? He's just wild. But I guess when you have that much money, you really have zero concerns. When I first met him,
Mike Tyson? He had to punch Zach in the face. He kept kind of doing it wrong for Cameron. So I remember going, no, Mike, just come over here. And Zach's standing here. And I'm sort of showing him how to throw a punch. And without missing a beat, he goes, oh, this is great. I'm getting boxing lessons from the captain of the Jewish debating team. Mike Tyson, he had to punch Zach in the face. He kept kind of doing it wrong for Cameron. So I remember going, no, Mike.
Probably not. This is probably during brain development. Roll the credits.
Birds' tongues consist of 5 bones.
Jesus Christ.
When she received a Christmas gift that she always wanted, she couldn't believe it. Her mother asked what it was.
Trying to move his finger. Oh!
You all right? Yeah, I think you're going the wrong way. Yeah, and you're not using a crosswalk. You're right.
Whenever this kitten sees her older sister walk in the room, she lays down on the ground like this.
After this cowboy passed away, his final wish was to have one last ride on his favorite horse. So his family made it happen for him. And his
Good morning, and welcome to Taking Another Turn.
Wait, that guy just walking so casually.
That makes no sense.
I'm going to put a little on your hand.
Do that Oprah did.
Yeah.
How come it's red?
I'll show you in a sec, Steve. So this is made from...
Look, the wrinkles has just disappeared.
so it's made...
And do you need
Oh, I'm so horny for me. Oh, okay.
Wow.
Look above.
Yeah. Yeah. Yeah.
The average strawberry's been sprayed over a dozen.
Body snatching.
My name is Bin Lekau.
1968.
Pay close attention to what you're about.
That's the M87 black hole. So what you're seeing there is the emission.
Oh, that's her. La 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 la.
Recently, I made a video about whether gravity was a force. I was scrolling through the comments, always an eye-opening experience, and I noticed one question in a specific comment. This individual asked if the weak nuclear force was a force in the usual sense of the word. It turns out that this is a common question with some interesting surprises, and that means you should sit back because I have a story to tell. To determine whether something is a force, you first need to know what it means to be a force. While there are technical definitions for this video, I want to use a common sense one. A force is something that either causes an object to move or would cause something to move if it wasn't held in place. There are several known fundamental forces. While the question of how many forces exist is more subtle than you think, it's common to say that scientists know of 4 forces. They are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity, of course, holds us here on Earth. It's a force because if a cat misses a jump, it falls. Gravity satisfies the simple definition and brings us thousands of funny cat videos. Electromagnetism is also a force. After all, a magnet, which is part of electromagnetism, can pick up small metal objects, so it's a force too. The strong nuclear force holds the nucleus of atoms together. We know this because the nucleus usually contains several protons, all of which have a positive electrical charge. In electromagnetism, when you have 2 charges with the same sign, they push away from one another, which would blow the nucleus apart. Therefore, nuclei wouldn't exist if there wasn't a stronger force holding the nucleus together. So that's 3 of the 4 forces. However, when scientists like me talk about the weak nuclear force, we usually just say, and the weak nuclear force is responsible for some forms of radioactivity. And that's completely true, but causing things to decay doesn't seem to satisfy the simple force definition we're using here. So that's the origin of that YouTube comment that made me decide to do this video. Does the weak nuclear force cause something to move? Well, to begin with, let's talk about how the weak nuclear force works at the quantum level. Like all quantum forces, the weak force occurs when a matter particle emits a force particle that then flies off to another matter particle that absorbs it. In the weak nuclear force, there are actually 2 force-carrying particles. There's the electrically neutral Z boson and the electrically charged W boson. In the case of the weak nuclear force interaction, some subatomic particle, say a quark, can emit a Z boson. The Z boson then zooms over to another quark, which absorbs it. That's at least one way in which the weak nuclear force is transmitted. So now let's get down to brass tacks. When the quark emits the Z boson, the quark will recoil. If it's initially stationary, it will move in the direction opposite the motion of the Z boson. It's not very different from when you're in a boat and throw a heavy sack off to one side. If you do, the boat moves. And when the other quark absorbs the Z boson, it also recoils. Not so different from someone catching that sack tossed from a boat. So, if a Z boson is exchanged between two quarks, the two quarks can move away from one another, and therefore, the weak nuclear force definitely satisfies the classical, intuitive definition of a force. That's the basic answer. However, the weak nuclear interaction is much more interesting than just being a force. For one thing, both the W and Z bosons are very heavy. They're in the ballpark of 100 times heavier than a proton. It turns out that the mass of the W and Z bosons is why the weak force is so weak. It's weak because weak force interactions are rare, not because it only pushes a little. To see that, let's dig a bit into this, and I should warn you, there's some quantum stuff involved. Let's take the W boson as an example. If you look up the mass of the W boson, you'll see that it's 80.35 GeV, or just shy of 86 times as heavy as the proton. When you're talking about quantum particles, stating the mass is only part of the story. In reality, every subatomic particle has a range of masses, with some having a large range and some having a small one. In the case of the W boson, the range is generally between 78.3 and 82.4 GeV. If you find a W boson, there's a good chance that it will have a mass in that range. You can see here a curve which kind of demonstrates this. Where the curve is high, it's likely the mass you find is there. Where it's low, it's unlikely that you can find a W boson with that mass. However, the numbers I just mentioned gives you the typical range. Other masses are possible, with rapidly decreasing probability. In the kinds of radioactivity that involve a W boson, what's needed isn't a W boson with a mass of about 80 GeV. What's needed is a W boson with a mass more like 0.001 GeV. And as we can see from the graph here, that's in the you gotta be kidding me territory. W bosons with that mass are like crazy rare. So this explains why the weak force is weak. It's just that W bosons with the required mass are super rare. If a rare weak force interaction actually happens, it really isn't all that weak. It has similar effect as the other known quantum interactions. Since I'm talking about the weak force, I should probably tell you something that is unique about it. It turns out that the weak force is the only one that can change a particle's identity. For example, when the top quark decays, it does so via the weak nuclear force. What happens is the top quark emits a W boson, and when it does, it turns into a bottom quark. When the bottom quark decays, it also splits out another W boson and becomes a charm quark. This identity-changing behavior is usually what scientists talk about when they discuss the weak force. It's not that the weak force doesn't push particles around like all forces do. It's that only the weak force can change particles' identities. So that's the thing we mentioned, because come on, that's just kind of awesome, you know. So what's the bottom line? The weak force can push particles around, so it's definitely a force like the others are. It's also not really weak so much as it's rare. And it's also the only force that can change a particle's identity when it decays. When you get right down to it, the weak force is just very, very cool. Okay, that was an interesting topic. It's easy for non-experts to get the wrong idea about various particle physics concepts. After all, when guys like me make science videos, we sometimes cut corners and we don't always say everything we know. If you like this deeper dive into the nature of the weak force, please like the video and smash that subscribe button down there. And come back often to hear more about the mysteries of physics, which makes good sense to me because, well, as I'm sure you'll agree, physics is everything.
So I'm really perplexed by this W. Was it a W? What was exchanged at the end of the day? What was being exchanged?
Weak force occurs when a matter particle emits a force particle that then flies off to another matter particle that absorbs it. In the weak nuclear force, there are actually two force-carrying particles. There's the electrically neutral Z boson and the electrically charged W boson. In the case of the weak force, the force occurs, well, to begin with, let's talk about how the weak nuclear force works at the quantum level. Like all quantum forces, the weak force occurs when a matter particle emits a force particle that then flies off to another matter particle that absorbs it. In the weak nuclear force, there are actually two force-carrying particles. There's the electrically neutral Z boson and the electrically charged W boson. In the case of the weak nuclear force interaction, some subatomic particle, say a quark, can emit a Z boson. The Z boson then zooms over to another quark, which absorbs it. That's at least one way in which the weak nuclear force is transmitted. So now let's get down to brass tacks. When the quark emits the Z boson, the quark will recoil. If it's initially stationary, it will move in the direction opposite the motion of the Z boson. It's not very different from when you're in a boat and throw a heavy sack off to one side. If you do, the boat moves. And when the other quark absorbs the Z boson, it also recoils. Not so different from someone catching that sack tossed from a boat.
So it's a Z
The Z boson
boson.
is exchanged between two quarks. The two quarks can move away from one another, and therefore, the weak nuclear force definitely satisfies the classical, intuitive definition of a force.
Fantastic. That's the
However,
basic
the
answer.
weak nuclear interaction is much more interesting than just being a force. For one thing, both the W and Z bosons are very heavy. They're in the ballpark of 100 times heavier than a proton.
Jesus.
It turns out that the mass of the W and Z bosons is why the weak force is so weak. It's weak because weak force interactions are rare, not because it only pushes a little. To see that, let's dig a bit into this, and I should warn you, there's some quantum stuff involved. It's all kind of mind-blowing. Let's take the W boson as an example. If you look up the mass of the W boson, you'll see that it's 80.35 GeV, or just shy of 86 times as heavy as the proton. When you're talking about quantum particles, stating the mass is only part of the story. In reality, every subatomic particle has a range of masses, with some having a large range and some having a small one. In the case of the W boson, the range is generally between 78.3 and 82.4 GeV. If you find a W boson, there's a good chance that it will have a mass in that range. You can see here a curve which kind of demonstrates this. Where the curve is high, it's likely the mass...
Okay, I gotta go. This is very interesting. All right. Okay, everyone. I'm cutting the stream. I'll see you later. Bye-bye.